This photograph shows a 1940s medical ward dealing with the harsh reality of global disease. Treating patients at this scale requires the reliable mass production of complex pharmaceutical drugs like antimalarials. And this is a crop duster blanketing an agricultural field. Protecting the global food supply requires completely different chemical tools, like the synthetic herbicide 2,4-D. Look at the molecular structures of both an anti-malarial drug and a modern herbicide side by side. Despite their different uses, they share a foundational structural trait, an aryl halide, which is a specific configuration where a halogen atom is attached to a 6-carbon benzene ring. Mass-producing these specific structures for global use requires a highly reliable way to bolt a halogen atom onto a benzene ring on an industrial scale. You might wonder why chemists don't just toss benzene and a halogen into a vat, heat it up, and let them react directly.
This animation shows what happens with direct iodination. Without an oxidizing agent to consume the byproducts, the reaction stalls and runs in reverse, breaking down the newly formed molecule almost as fast as it is made. Direct fluorination presents the opposite problem. The interaction is far too violent to safely control, making it entirely impractical for laboratory synthesis. Because directly attaching these atoms is either ineffective or dangerous, chemists have to use a multi-step detour to engineer these molecules. This chemical equation starts with a cheap, easily accessible starting material, a primary aromatic amine known as aniline. When aniline is mixed with sodium nitrite and cold mineral acid at near freezing temperatures, between 273 and 278 Kelvin, the chemical change begins. The cold mixture converts the stable amine group into a new functional group, forming a diazonium salt. This new diazonium group is unstable. It vibrates with excess energy, struggling to hold its form. That instability is the goal. The molecule is now acting like a loaded spring, primed and ready for the substitution step. To trigger the release of that spring, a copper-1 salt catalyst, such as cuprous chloride or cuprous bromide, is introduced to the mixture. The unstable nitrogen group bubbles away as nitrogen gas. This departure leaves a molecular vacancy for the halogen to lock securely into place. The final result of the sequence is a stable aryl halide, in this case chlorobenzene. By utilizing this two-step swap, chemists bypass the inefficiencies of trying to force a halogen directly onto a benzene ring. Chemists prefer this exact sequence, the Sandmeyer reaction, over the Gattermann reaction, which uses copper powder, because the Sandmeyer yields more usable product. This flowchart shows a known shortcut for creating aryl iodides. The copper catalyst is not necessary here. Simply shaking the diazonium salt with potassium iodide is enough to force the swap. Fluorine has its own alternate pathway, called the Balz-Schiemann reaction. It relies on the same logic, but requires treating the diazonium salt with fluoroboric acid instead of copper. Industrial chemistry requires selecting the specific catalytic tool suited for the halogen required. Starting with a basic, inexpensive amine, this reaction sequence safely and predictably engineers a versatile aryl halide building block. This photograph of a production line shows exactly where that chemistry goes. This precise sequence is the industrial standard for producing these active ingredients at scale. Generations of chemists have stood in laboratories just like this one, using the logic of the Sandmeyer reaction to scale up solutions from a single beaker to mass production. The Sandmeyer reaction demonstrates that by controlling the behavior of these reactive intermediates, we can predictably assemble the specific chemical structures that global medicine and agriculture rely on.